When we were learning algebra, we first learned what a variable was, and then we learned how to put variables together into what we called expressions. Finally, we learned what an equation was, and eventually how to solve them. In this video, we're going to be talking about polar equations. We know what the variables are now, r and theta, and we know that we can establish relationships between these two variables. So now it's time to talk about equations that involve those two variables. So let's start with an example of an algebraic equation. But very quickly, perhaps you'll remember that x equals r cosine theta and y equals r sine theta. I can take this equation and rewrite it in terms of r and theta. Since x equals r cosine theta, I'll replace the left-hand side with that. And of course, x was squared, so now r cosine theta has to be squared. And the right-hand side is 4y, so I'll make that 4 times r sine theta. So what I've done is convert this algebraic equation into a polar equation. And that's really all there is to it, except that once we know how to do this, there may be other things we can do with this equation, eventually including graphing it. That's for the next section. So we'll get to that eventually. But for now, let's take a look at what happens when we expand this. Algebraically speaking, this is equivalent to r squared cosine squared equals 4r times the sine of theta. Now, normally when you have a variable on both sides of the equation, I discourage students from dividing both sides by that variable. For example, if I had x squared equals 2xy, it's tempting to want to divide both sides by x. But if you do, you may just have divided by 0. If x could equal 0 in this instance, then you've just divided by 0, and you're not allowed to do that. So normally we say don't divide by a variable, but instead make sure you have the whole expression on the same side of the equal sign and then factor out that variable. Oops, I forgot to factor out my x. Now I can see that in fact, yes, x does equal 0. That's one of the solutions to this equation. And I factored out an x but didn't factor out, I gotta get rid of that squared. That's what happens when you go too fast. I also have 2 minus x minus 2y equals 0, and I can go from there. So normally it's not a good idea to divide out by a variable because you might be dividing by 0 if you do that. In this case, we're going to let you get away with it though, because r is a radius. And while it's theoretically possible to talk about a circle with a radius of 0, it's not very practical to do so. So now I have r cosine squared theta equals 4 sine theta. And now if I divide both sides by cosine squared, I get r equals 4 sine theta over cosine squared theta. And I suppose I could write that as 4 times sine theta over cosine theta times 1 over cosine theta, just splitting out that cosine squared, which would give me 4 tangent theta secant theta. Now, I did this last part, changing this expression into this expression into this expression, primarily just to remind you that identities are still valuable. This is still a valuable skill to be able to use. But really, all I've done here is change this, first of all, from an xy equation into an r theta equation. And then importantly, I have solved for r, because in terms of how we think about trigonometric polar equations, we think of r as the dependent variable and theta as the independent variable. So this equation is now a function of r in terms of theta. Analogously, what we've usually done in the past is rewritten expressions like this so that they were y equals something in terms of x. This would give me y equals x squared over 4, or 1/4 x squared. And oftentimes, you'll see that written as either f of x, the function of x, defined by x squared over 4, or sometimes even y of x is x squared over 4. So this expression is a rewrite of this this equation is a rewrite of this algebraic equation in the same way that this equation is a rewrite of this equation, so that the variable r is by itself on the left-hand side, in the same way as we wanted y to be by itself on the left-hand side of this algebraic expression. Okay, that was just the example from your textbook. I'm on page 591, but let's take a look at another example of a similar type of problem. Here, we're asked to rewrite the equation y equals 6x squared, which is currently a Cartesian equation, or an equation in rectangular coordinate form. Rewrite that as a polar equation. I'm going to start by copying the equation y equals 6x squared, and then I'm just going to remind myself that x equals r cosine theta, and y equals r sine theta, and I'm going to do that substitution. Since y equals r sine theta, the whole left-hand side can become r sine theta. The right-hand side is 6x squared, so that becomes 6r cosine theta squared. Looks pretty similar to the last one. It really is, actually. R sine theta, therefore, equals 6r squared cosine squared theta. Now, I want to write this in terms of r. So I want the r by itself. When I divide both sides by r, I'm not going to have an r left on this side. I am going to have an r left on this side. So I'll start by dividing both sides by r. In your textbook, they also make the note that since r, they don't say it this way, but since r is going to be, the only r left is going to be the one on this side, we want that to be by itself. Let's also divide by 6 and by cosine squared. Of course, I need to do that on both sides. So the 6 is gone, the cosine squared is gone from the right-hand side, and one copy of r is gone. On the left-hand side, r is gone. And remember that the reason we can do this is that if r is 0, then we don't really have a circle. A circle with radius 1 might look like this. A circle with a radius 1/2 might look like this, 1/4, an 1/8, and so on. And if a circle has a radius of 0.001, it might look like that. The closer r gets to 0, the closer you get to having just a point. And we call that the degenerative case. If the radius of a circle can vary, like I've done here, it's varied from 1 down to 1/2, down to 1/4, and so on, then when the radius gets down to close to 0, you still have a circle. But when it actually equals 0, you no longer have a circle, you have a point. That said, we can still write the equation x squared plus y squared equals r squared, where r is 0. So this is technically a circle, but it's not a very interesting one. So that's why we can get away with dividing by r, even though r might be 0. Okay, continuing, all I have left on the right-hand side now is r. So I'm going to write that on the left-hand side. And what's on the left-hand side, I'll write on the right-hand side. Sine of theta over 6 cosine squared of theta. That's equivalent to 1/6 times sine over cosine times 1 over cosine. So again, I have this time 1/6 times the tangent of theta times the secant of theta. The substitution's usually pretty easy. Wherever there's a y, put an r sine theta. Wherever there's an x, put an r cosine theta. Do some algebra. The trick is remembering that the goal is to get an equation that's written as r in terms of theta. So I have an r on the left-hand side, and thetas, all the thetas are on the right-hand side. Now, there's a theta here, but that's because I've rewritten this as a function, r in terms of theta, in the same way as I would have written y in terms of x, like this, or sometimes like this, but that's a specialty notation. And technically, you don't need the of theta part. You can write your equation just r equals tan theta secant theta in the same way that we often write y equals 6x squared. So that's how you take a Cartesian equation and write it as a polar equation. But what if I give you a polar equation and ask you to write it as a Cartesian equation? Here's our polar equation, r equals 6 sine theta. Let's recopy it here. And then one thing that I can do is remember that r is equal to the square root of x squared plus y squared. And theta is equal to the inverse tangent of y over x. And I can try just doing that substitution. Let's go ahead and try that. R is equal to the square root of x squared plus y squared, so my left-hand side becomes the square root of x squared plus y squared. And then I have on the right-hand side 6 times the sine of theta, where theta is the inverse tangent of y over x. Now, technically, this equation is in Cartesian form, but I still have some trigonometric stuff going on here. So I could do this the hard way and see if I could figure out if tangent is opposite over adjacent, that's y over x. The third side is going to be the square root of x squared plus y squared, and because that's what r is anyway, and then take the sine of that, that's y over this, y over the square root. Then I can rewrite this as the sine of the inverse tangent of y over x is y over the square root of x squared plus y squared. Now if I multiply both sides of this by the square root of x squared plus y squared, I'm not sure I can squeeze this in here, it happens that I get the square root times the square root, then they're the same thing, so I could write that as the square root of x squared plus y squared squared, which is just x squared plus y squared. On the right-hand side, those cancel, and I get equals 6y. That's one way to do it. It's a little messy, but it's certainly legitimate. Will it always work? Not necessarily. So let's take a look at a slightly different strategy that I think you'll find a little bit easier to work with. I'm going to rewrite the question or the problem, the equation that I was given, r equals 6 times the sine of theta. And then recognizing that what I'd really like is for this to say r sine of theta, because r sine of theta is y. So if I introduce an r in there, if I multiply the right-hand side by r, then I must also multiply the left-hand side by r. So now I can change my right-hand side to 6 times y. And I can also change my left-hand side to r squared, because x squared plus y squared, if you square both sides of this equation, you get r squared. So I'm going to change my left-hand side to x squared plus y squared. And I got exactly the same answer here as I did up here. Not only is it simpler, but this may not always work. So this is what I would call the brute force method, and this is what I call the clever thinking method. This is actually the method your textbook suggests, and it makes sense. It's hard to recognize that you need to multiply both sides by r, but if you remember that what you want is to find things that look like r sine theta or r cosine theta, because then you can replace r sine theta with y. So it's kind of doing a reverse xy substitution instead of doing an r theta substitution. Now that we have our equation in the form that we want it, let's take a look at how we might figure out what the graph of that thing looks like. What is this polar equation? Where am I? R equals 6 sine theta. What is that? What does the graph of that look like? Well, if I could graph this, then I'd be able to tell you. And the left-hand side makes me think it's going to be a circle, but the right-hand side is not just an r squared, so I need to figure out a different way to write it. Let's get rid of this brute force method and just keep the method that we found that was a lot simpler to work with. And then I'm going to keep playing with x squared plus y squared equals 6y. In fact, I'm going to start by subtracting 6y from both sides. That gives me x squared plus y squared minus 6y equals 0. And now, on one hand, it's tempting to factor a y out here, but on the other hand, it's tempting to complete the square. Now, I know a lot of students don't like completing the square, but it's actually a really handy way to get to the right form or the easy form of a way to graph this thing. So by way of reminder, completing the square on y squared minus 6y equals 0 would mean adding to both sides a quantity that would make this a perfect square. That perfect square is going to be y minus 3 all squared. The reason I know it's y minus 3 all squared is because I've done this, I might not be exaggerating if I say 1,000,000 times. I know to take half of 6 and square it. That's plus 9. If I do that to the left-hand side, I must also do it to the right-hand side. And now, this thing here, this left-hand side, factors as y minus 3 squared. The right-hand side becomes equals 9 instead of equals 0. And that's okay. In the case of the circle, in the case of the equation that I have down here, I'm going to do exactly the same thing, except that I have an x squared hanging off the side there. So I have x squared plus y squared minus 6y equals 0, and I'm going to add 9 to both sides, factor just this into y minus 3 squared. I still have an x squared over here, and now my right-hand side is 9. Now, if you remember from algebra how to graph shifted things, and we've done it in this class as well, I have here the equation of a circle, which would normally be x squared plus y squared equals r squared. I can tell what my r is going to be. It's 3. And my x squared looks normal, but my y has been shifted. So I'm going to take a circle that would normally be here with a radius of 3, and I'm going to shift it the opposite, because this is inside the parentheses with the y, the opposite direction of this 3, this minus sign. So I'm going to go up 3, up and down because I'm in the y direction, and I'm going to go up because this negative tells me I need to go in the opposite direction. So I'm going to go up to 3 and recenter my circle here, and then draw the circle. That's not a very good circle, but it'll do. So if I were now to erase this white circle, the yellow circle that's left, this is the circle that is the graph of this equation. But that's the same equation as this in a different form. And this is the same as this one in a different form. And in fact, this is the same as this original equation, just in a different form. So what I've done here is I've graphed r equals 6 sine theta with this yellow circle. So that's what the graph of a circle looks like in polar coordinates. Now, if I were to graph r equals 6 cosine theta, it would end up over here, interestingly enough. We'll play around with that some more in a little while. But r equals 6 sine theta also tells me what the radius of my circle is going to be, and that's half of 6. The reason that happened is that when I converted it to rectangular form and then completed the square, I added half of this squared to both sides. It was the thing I took half of that got squared. That became my r squared. So my r is half of this number, which is half of this number, which is half of this number, which is half of this number right here. Now, that's all we need to do in this topic, because the entire next section is graphs of polar equations. So we're going to be talking a lot more about graphs of polar equations. So we can curtail our conversation about graphs of polar equations here. In this topic, what we've really done is learn how to identify polar equations, convert from rectangular equations to polar form, and from polar equations to rectangular form. Rectangular and Cartesian are synonymous. So that's all we need to do here. I'll see you in the next section.